Thank you. Yes, so it's a pleasure. Thank you for inviting me to speak here in this workshop. So I will speak about some exactly solved models of quantum many-body chaos. And here is a short kind of summary of what I'm trying to address in this 30-minute talk. Probably I will go through some things very, very briefly, but I hope there will be some room for discussion afterwards. I also should apologize for those people who have recently heard maybe a previous version of this talk, which would have a lot of overlap with today's, but I'd like to find some time to stress most recent results also. So I mean, also here there are two heroes of this project, of this endeavor, Bruno Bertini, who was a postdoc with me for the, let's say, 3 years until last fall, and Pavel Kos, who is finishing his PhD on the topic. And basically, the upshot of these results is basically trying to find simple, exactly solvable models of quantum many-body dynamics in a very similar spirit to, let's say, exactly solved models of classical chaotic dynamics, such as Baker and cat maps. I mean, for those who have had some background in classical dynamical systems theory or chaos theory, I mean, they know that, you know, if you teach this dynamical systems, you have a couple of models which you can basically, you know, solve on the blackboard for students, and yet they are chaotic in the sense that the trajectories are unpredictable. I mean, one could actually speak of some sort of statistical solvability of these models. So, for example, one can compute correlation functions exactly, and so on. And I mean, kind of thinking about many-body dynamics for many years, I mean, I was missing this type of models in many-body physics. I mean, we are all aware of, I mean, we all like integrable systems, even free systems, you know, they are kind of really popular because people can solve them exactly, but they are not very typical. Now, the question is, I mean, do we have a typical examples, let's say, ergodic thermalizing dynamics, which would be exactly amenable to exact analytical computations? And that a couple of models that I'm going to talk about in this next 30 minutes are precisely that. So what we will do is we will solve a couple of things for these models. I mean, first of all, I will define these models and try to define them in as general way as I can at the moment. I mean, this is not how we historically proceeded with these results. I mean, first there was this kicked Ising chain, which still, I mean, we like and some people like, but it's a particular singular isolated fine-tuned model. And then this model can be embedded into a larger class of models, which we call dual unitary. I explain exactly what it is. And that's, as I say, it's much broader class, and it basically has all the nice goodies of the kicked Ising model. And for example, I will show you how to compute general correlation functions, general in a sense of any local observable in arbitrary spacetime between, let's say, two-point correlation function between two arbitrary spacetime points. And then I hope the time permits, I will try to address some more recent results on operator spreading and structural stability of this type of ergodic dynamics. So I will try to understand computation of correlation functions around the ergodic points, around the exactly solvable ergodic points in perturbative ways. So the idea is that this might have kind of finite radius of convergence, so which would be very different than expanding around free or integral theories. I mean, here I would like to, because probably I won't have much time to stress this point later in my talk. So I mean, I think you should raise your, I mean, at least I raised my eyebrows when I first thought about this. I mean, how could this be possible? But that's really, I mean, if this is, of course, this is at the moment, it's still a speculation, which is just corroborated by one single very particular result, which I will show you at the end of my talk. But still, this could be a general kind of strategy, or it's a general behavior of ergodic systems. I mean, we all expect that ergodic systems are structurally stable in the sense that if you look at the neighborhood of ergodic system in some parameter space of Hamiltonian models, it will be ergodic as well. It's different from integrable systems, which is isolated point. If you perturb it, it becomes, you know, pre-thermalizing and then eventually thermalizing to a Gibbs state. So, so I mean, in that sense, these models can be much more generic. And that's why this kind of analytical calculations can be even more far-reaching. But you know, that's at the moment is kind of a vision.
Sorry, Tomasz, we have or no, disappear. Alexei was raising the hand, but then so probably there are no questions. So yeah, please go ahead.
So let me just go straight to this simple class of models. I mean, basically, the models I'm going to address in my talk are Floquet. I mean, are basically belong to a general category of quantum circuits, local quantum circuits, which are built as brickworks. These models can be, in special cases, when all the gates are the same, also considered as Floquet systems, because one layer of the gates can be sort of as one period's time evolution propagator. And of course, these models can be thought of also as models of general Hamiltonian systems in some sort of Trotter limit, if you want. But that's not what one should keep in mind here, because the Trotter limit usually don't work nicely with what I will now present, is the unitarity. So you should think of a discrete time dynamical system, which is generated by some two-body gate. So let's just discuss the property of this gate. So this gate is a two-particle scattering operator, if you want. It maps states I and j to states k and l via some unitary u, right? And I will just draw these gates with wires under 45-degree angles, because I would like to consider this simultaneously as gates which propagate bottom up, which would be temporal gate, and gate which propagates left to right, which I would call spatial gate. So now I will consider a particular class of gates which are unitary in both ways. So for example, I will define this, what we call a dual gate, space-time dual gate, u tilde, which is different from u, which is just, you know, which is defined as a reshuffling of indices of matrix U, right? We just consider I and k as input and j and l as output. And what we require as for the gate to be dual unitary is that both of these gates, u and u tilde, are unitary. So of course u should be unitary from the outset, but you know, after you also require that u tilde is unitary. The question is, what does this buy you? And I'm trying to convince you, yes, this gives you a lot of additional structure. I mean, this basically gives you that you can solve a lot of stuff. So first, let me just try to introduce you some simple diagrammatics, which helps to contract or simplify quantum circuit expressions for correlation functions and operator entropies and so on. So for example, you can just imagine your gates to be depicted as a red box. Then the Hermitian adjoint of the gate, let's assume, let's denote it by a blue box. Then the unitarity, I mean, of course, imagine again, time goes bottom up. So in is here, out is there, then compose it with the inverse, Hermitian adjoint, then you get straight lines, right? Just identity operator. And similarly, if you exchange, you will do that. So this is sometimes I would refer to this as fusion rules or forward fusion rules. But aside from that, you also have the sideways fusion rules, which are basically just implementation of what I call the dual unitarity. This I will sometimes refer to as dual fusion rules. So now let me just consider now building a quantum circuit out of these gates. Again, before you start to think about your favorite models and whether you can recast them in this way. What I will say immediately generalizes to completely inhomogeneous circuits with temporally and spatially dependent gates, if you want. So noisy and disorder can be easily accommodated for. But for simplicity, I will consider all these gates to be the same, just to give you simple results. But I mean, of course, you can define dual unitary disordered gates, disordered circuits, or even noisy circuits, or quasi-periodically driven circuits, if you want. Yeah, so on and so forth. So this is basically the standard way people build these brickwork circuits, right? So we start with a layer of two particle gates, which is just a tensor product. Again, remember that times goes up. And then you just compose it with a shifted array of gates. So this would be like a one layer of brickwork. So iterating it by 2 time steps, you get basically a circuit for, let's say, depth t equal to 4 or 2 time steps of size L equal to 6 or 12 gates. 12 qubits if you want. And similarly, you can define now, I mean, just looking at this picture sideways, we can define it as a quantum circuit, which is again unitary, because by virtue of dual unitarity, this evolution is also unitary. I will denote it now by this W, U with double lines, tilde, which is again composed as a quantum circuit using this tensor product and the shift operator in time now, using this utility. And then clearly we have what you might refer in a bit pretentious way, duality of traces. So you can think of, a trace of the propagator of this whole circuit as a kind of partition function on the torus. Right now, time is doing the traces. Time is periodic, and assuming that also space is periodic, then this is very democratic between exchanging space and time. So you can think of trace of u to the t being either written as such or as trace of u tilde to the L. Right? I mean, this is of course very familiar concept in statistical mechanics. I mean, this is just like computing partition function in two different ways using row transform matrix or column transform matrix. But now this is not statistical mechanics. This is quantum dynamics. So these transform matrices are unitary operators. And now what we are asking is that they are unitary not only in time but also in space. And that again, I mean, I advocate this. This is of course might seem innocent, but it basically has far-reaching consequences. One of them is that we managed to use that unitarity of the dual evolution to prove that the spectral statistics of Keith-Ising model conforms to random matrix theory in thermodynamic unit. So I mean, there is a bit of tricks with scalings of L to infinity and T to infinity, which I don't want to get into now, but I'm happy to discuss it in the discussion session. But if you are willing to take thermodynamic unit first, meaning that you don't ever reach Heisenberg times, but you just reach, if you want, spectral compressibility or long energy range spectral statistics, then you can prove that you have spectral statistics which conforms to random matrix theory for particular type of model which is unitary. And and just before describing this result, let me just, for those who have not seen this, just briefly outline what is the main concept that we try to calculate here. This is the spectral form factor, and that's basically the simplest spectral correlation measure, which is the 2-point spectral statistic. I mean, any 2-point spectral statistics is equivalent to any other, so they can be usually transformed to one another using some integral transforms. And the one which we like is this one which is simple in time picture, which is the spectral form factor, which is the Fourier transform of the 2-point level correlation function. So assume you define your, let's say, starting from a unitary operator. Now everything is of course for discrete time. So dynamics is, I mean, the spectra are given by eigenspectra of unitary operators, not Hamiltonians. Hamiltonians would be in principle time dependent, but since you have Floquet dynamics, you have to look at spectrum of the unitary. This I will denote as phi sub n. So this defines spectral density, and the 2-point correlation function of spectral density connected correlation function, which I denote as r of theta. And it's Fourier transform, simple Fourier transform on a circle. Then since we are on a circle with periodic boundaries, the natural Fourier argument is integer. So the time, of course, for Floquet is an integer period of multiple of the fundamental period. So imagine we measure everything in this fundamental period. So then time is integer. So this way we define this correlation function. I mean, the Fourier transform of the correlation function, and this is a 2-line calculation which I skip, but anyone can do it in 10 minutes in the break. You get a very simple expression that the spectral form factor, the Fourier transform of the 2-point spectral density correlation function, is just a double sum over the spectrum e to the IT phi with 2 different eigenvalues phi m and phi n, double sum. But this is just a trace of the u to the power t to modulo square minus delta function of t equal to 0, which is irrelevant for our discussion. So that's a really cool expression because it just gives you the spectral measure in terms of traces of the propagator of dynamics. So assume that you have access to this, and this is the kind of, if you want, some people would call it an average Loschner-Waco. I mean, an average return probability or return amplitude better. So starting from a random state, what is the amplitude, an average, to return to the same random states after time t? Average to random states. That would be like, if you want for an experimentalist protocol to measure. Now, of course, there is a caveat. This quantity is not self-averaging, so one has to consider some sort of averaging. Otherwise, this doesn't make sense. And these averagings usually can be quite innocent. I mean, usually people consider averagings of an ensemble of models, which is near a particular model of interest. For example, some disorder averaging with small, usually arbitrarily small amount of disorder is enough, or some other model parameter like some magnetic fields, or even some moving time averaging. Now, this is what random matrix theory teaches you about spectral form factor. It seems that it is a very sensitive spectral measure, meaning that it discriminates between Poisson statistics, which is uncorrelated levels, for which this double sum is basically a sum of random points. So one can use random walk arguments to derive what should spectral form factor be. And it turns out that then it should be just up into to first approximation, just a flat line for Floquet dynamics. And the flat line should be saturated to the value which is given by the number of levels, if you have noticed curly n. And you see, this is exponentially for a many-body system. This curly n is 2 to the system to the number of qubits. So this is exponentially gapped from values which you predict for chaotic dynamics. So this is possible, which people believe should be true for integrable. And for chaotic dynamics, you should get linear ramps. Now forget about your decay, because this happens only for continuous time dynamics. For discrete time dynamics, there is just ramp and saturation. And these ramps can happen with different slopes depending on your anti-unitary symmetries. So for no symmetries, you have unitary ensemble, it's slope 1. For unitary anti-unitary symmetries with square root 1, you have slope 2, which is orthogonal ensemble. And then, of course, people discuss very vividly also this second time scale. There is one time scale which already probably you've seen in passing, which is the number of levels. Basically corresponds to the dimension of the Hilbert space of the number of levels, which is the so-called Heisenberg time. So after that time, basically nothing can grow anymore, and things typically saturate around the plateau value, which is again given by number of levels. But for short times, there might be another time scale before which system cannot be described by universal theories, because short time dynamics usually is given in terms of there is usually some approximative methods to solve dynamics for short times, which are usually as getting better and better at a shorter time. So this cannot be, this cannot be equivalent to random matrices. I mean, these dynamics cannot be given by random matrices. So there should be times. Sometimes, for random systems, these times are associated with diffusion, and before diffusion reaches the ends of the system, you should get some different behavior. So these times are usually referred to by some, by the term tauless time, or if you have a system which is semi-classical, maybe more appropriate expression is the Ehrenfest time. But there is a time scale before which systems cannot be random, be universal. So I mean, the question is how you explain universal behavior of many-body system between tauless time and Heisenberg. And this is just, since I have just 30 minutes and I'd like to cover several aspects, I will not go into any details of the proofs. But I'm just quoting our most recent result, which is also the most complete one, which has been put on the archive in December, which is basically a theorem which describes spectral form factor for any, or essentially any dual unitary circuit of qubits. And not only that, actually any dual unitary circuits of qubits for particular class of multivolumetric class of dual unitary gates. But let's just assume these are qubits. For qubits, this is totally general. Well, I mean, let's say the theorem I quote here is not completely general, but we can generalize it also to completely random arrangements of two qubit dual unitary gates. So these boxes should be dual unitaries. Now, for example, this box, this is just to make it simple. Assume that these boxes are all the same. So red box is the same, orange box is the same. It might be that in the second half time step, the orange is different than red. But then you see you have these SU2 rotations, which are denoted by blue, and these blue shades are all different, meaning that these SU2s can be different, and this is basically the disorder over which we average. But now the point is that this theorem holds, and this theorem basically tells you that the spectral form factor and thermodynamic limit is equal to T, which is the linear ramp for unitary ensemble. Now, and this theorem only requires that the distribution over disorder is IID with non-vanishing variance, no matter how small, if you take thermodynamic limit first. And distribution is completely general as soon as it is smooth and non-singular. I mean, smooth in the sense that it contains a finite probability to capture identity. So the weight of any finite ball around identity is finite, and that's it. So I mean, basically the problem, and I'm sorry, I cannot go into any idea of the proof, but the first step of the proof is basically to recast the calculation of the spectral form factor, which is just this. right? This is just trace of the circuit to power t modulo square, which is a definition, average over disorder distribution. So this u are these single qubit gates, and we average over distribution of the u. But now the first step of the proof is to use the duality formula. So first you just write it in terms of two replicas, right? So now you can see that trace of the square of the traces as trace over two replicas. And then you do the duality trick. So it means you write it in terms of the space dynamics. Once you do the space dynamics, you can average locally because the disorder is IID. So then you have a transfer matrix. Now the rest of the proof is to count the number of eigenvalue 1 of this transfer matrix. And this can be recast as a simple algebra, straightforward algebraic problem in terms of the dimension of the commutant of some set of operators. So these are simple operators, single qubit and two qubit operators, which are translation invariant in time. Now the space is time. The lattice is now has number of points which is equal to time. And now you just count how many operators commute with all these operators. And you find that these are exactly all possible translations. And there is T such translations. So this is basically the idea of the proof. So now, of course, when you have, let's say this, this is here the proof is simple for the unitary case. When you have the orthogonal case, then you have to also worry about time reflections. And time reflections give you additional factor of 2 because you have not only translations, but also translations composed with reflections. Okay,
sorry,
now,
Tomaz, can you go one slide? I mean, here you are putting the disorder like, let's say, an on-site energy, right?
Right, yes.
Can you also put the disorder in the, let's say, in the unitary itself? I mean, in the dual unitaries?
Look, we can put, as I already said, I mean, there is a generalization of our result, which is also quoted in the last section of this paper, where we can arrange any random, when we can take any random
dual unitary
unitaries which are not swaps, for which density of non-swaps is positive.
Okay.
So swaps are bad. Swaps are bad. But the only thing we require that densities of non-swaps are positive. In terms of
okay.
And that's enough.
Okay.
Of course, we don't average over that. We average over single qubit unitaries, but if you want, you can just make random arrangements of these guys.
Okay.
The theorem goes through. Okay, now I have to speed up, I guess. How much time do I have, by the way?
Yeah, I mean, you have a bit of time in the sense that you can also go a bit further than 30 minutes.
I try to not use that too much of that, but yeah. Okay, so let me just go to our next kind of class of results, which is maybe more physical in a sense because it addresses observables directly. So let's try to see if we can compute correlation functions, right? And let's try to see how we can formulate computation of correlation functions in these dual unitary models. So suppose you want to compute objects like this. You take a class of operators which are local and trace Hilbert-Schmidt orthonormalized. So it means that A0 would be identity, and A alpha from 1 to d squared minus 1. D for me is the local Hilbert space function. So these are qubits, qubits. D equal 2 would be qubits. So D equal 2 would be Pauli matrices, D equal 3 would be Kalman matrices, and so on. So just assume that you can Hilbert-Schmidt orthogonalize them, and all are orthogonal to the identity, which means that all are traceless. So there's the A alpha non-zero are traceless operators. Now assume that you can place, now this is of course all written in kind of tensor product Hilbert space. So X and Y are two positions in your lattice. This lattice is periodic going from 0 to L. And I now decide that I designate points of the lattice by integer and half integer lattice sites. So integer are even sides, half integer are odd sides if you want. I mean, because there is this natural staggering. And it's at some point we thought it was nice just to use half integer lattice to discriminate that, but doesn't matter. Now, this would be the general correlation function, right? Now, the idea is just to write this correlation function as a contraction of a quantum circuit in terms of U's and U daggers. Now the question is, can we use our simple fusion rules, which I flashed at the beginning of my talk, to simplify these circuits? And now, before since I have a short talk, I will not go into details of the proof, even though it's fully diagrammatic. I don't have to write any formula, but still, I will just give you in words the proof. I mean, the proof is, what is the proof? What is the statement actually? The statement is that these two guys, this correlator, can only be non-vanishing if these two guys stand on the same light ray, meaning if these two ends are connected by this line, or they would be connected by that line. Why is that? Well, the reason is that because we have dual unitarity, we have causality. You know, I mean, when you have unitary dynamics with these brickwork circuits, this is a quantum cellular automaton. So the information propagates by maximum speed 1. So everything is connected to everything. All the correlations are confined in the causal cone, which opens at speed 1. But now, since we have dual unitarity, we have another causal cone, which goes in space direction, also at speed 1. So basically, correlations can only propagate, information can only propagate along the intersection of these two causal cones, which is the two light rays, which I just designated by my mouth. So basically, just implementing this idea, or if you want, implementing fusion rules, which I discussed in my first slide, you end up with the only non-vanishing correlation function between A alpha and A beta, which is assuming that I'm sitting on one of the sublattices, which is going strictly right ways. And it goes exactly by t sides in t time steps. Right? But this guy is given in terms of completely positive trace preserving unital map. This one, which I call M+. So basically, this is just the iteration of CPTP. Right? So now we basically identify dynamics of a 1 + 1D interacting coherent non-dissipative system with the dynamics of a 0D open dissipative qubit quantum particle. So now I see this correlation function now is just expressed in terms of iterations of CPTP, right? It's just this curly M is CPTP, completely positive trace preserving map, which you apply to initial operator, you apply it to t times, and you take Hilbert-Schmidt scalar product with the final operator. Right, and now of course, everything you want to know about correlation function is basically in the spectrum of this CPTP. Now this spectrum of course, can be anything in the unit disk. I mean, these guys are non-expanding maps. So the spectra are within unit disk. They can be on a unit circle or strictly inside. And depending on that, you know, you can have different kind of people in chaos theory, they would call different, I mean, they have full hierarchy of ergodic behaviors. So you can have non-interacting dynamics, for example, even a swap. Swap would be the most pathological or the most non-ergodic case where all the eigenvalues of the CPTP are in unit circle, at 1 actually. Here, the CPTP has a spectrum which is all eigenvalues at 1. Now you can have non-ergodic dynamics, but still could be non-integrable where at 1 eigenvalue would vary. Of course, there is always a trivial eigenvalue which corresponds to unit operator. This has to be because of the unitality of the channel. But one can also ask if there are additional non-trivial operators, which are at 1, and these would correspond to conserved quantities, which are local. This would correspond to some sort of partial integrability, if you want, but it cannot be, it need not be a complete integrability. So there are examples of circuits which have what we call solitons, but they are not integral. And then you can have ergodic but non-mixing behavior when some eigenvalue is at unit circle, but not still on the boundaries of the unit disk, which means that you will not decay, but you can oscillate. I mean, again, people would call this a time crystal, right? And when all eigenvalues are within unit disk, then this would be a generic behavior, which would be thermalizing, ergodic, and mixing. Okay, you can have all that examples. I will not give you all. I mean, I will just flash through a couple of examples, but the purpose of that slide is just to give you a simple classification of all possible dual unitaries for qubits. I mean, it turns out that for qubits, now you can ask, is it possible to enumerate or parameterize all dual unitary gates and how special they are? Now, it turns out that for qubits, you can do that. Actually, you can start from this simple representation of any SU4 gate, right? For 2 qubits, you have representations of SU4, and all possible SU4 matrices can be written as a Heisenberg gate times tensor product of 2 SU2s on the left and the tensor product of arbitrary 2 SU2s on the right. And if you want also U4 rather than SU4, you can add a phase. And now, if you ask for dual unitarity, in dual unitarity only gives you kind of a codimension 2 submanifold in this U4, which is you have to fix the 2 guys in the Heisenberg gate to pi over 4, 2 parameters, right? And that's it. So you see, you have still multi-parametric manifold of dual unitaries, which allows you to play lots of, you can find lots of models which look like pretty innocent generic models in this class. Of course, they're not generic after you see this these results, but still. So, I mean, examples: swap gate, Heisenberg gate for pi over 4, jx, jy equal pi over 4, and also the self-dual Kick-Tisink model, which I mentioned a couple of times, can be written as a self-dual, as a dual unitary gate.
Sorry, maybe you said, but I lost. What do you mean by maximally chaotic in this case? That is related to the Lyapunov exponent, or?
Yes. Well, the Lyapunov exponent is a bit difficult because we have qubits. I mean, it's hard to associate it to some sort of Lyapunov exponents. But we can definitely show that the operator growth entanglement, and let's say,
okay.
I will quickly mention what we can say about, let's say, growth of entanglement of entropy and operator spreading, and that is maximal for that.
Okay.
What I mean by that is that its growth is maximal possible for qubits. Okay, so now that's a slide which I probably want to skip. That's just let's say more speculative slide. What we can say about generic systems. I mean, just to maybe I still can spend half a minute on that slide just to give you the motivation. See, I mean, one can view this kind of results as a proof of ergodicity, so which might be extended away. I mean, if you kind of believe my kind of vision that these things can be perturbatively stable, then you can try to approach this ergodic side of the localization transition using these methods, right? The question is where would this fail, right? If there is an MBL transition, then somewhere this should fail, right? There should be a finite radius of convergence, and this is something. I mean, this to me is kind of very catchy way of thinking about this, but of course it's very hard to make precise statements. So I mean, I have some preliminary kind of numerics which might suggest something, but some people have other conjectures. For example, there is a paper by Garat and Choka which addresses similar things. I mean, people define this so-called spectral Lyapunov. I mean, they found the catchy name for that. They call it spectral Lyapunov exponent. But that's just the way spectral form factor behaves in terms of spectrum of this dual transfer matrix. So the eigenvalues of the dual transfer matrix. Anyway, so I think, again, I'm sorry I speeded. I hoped I would have more time for the last section, so I probably have to just go through it in a few minutes. But anyway, so I mean, since you ask, I mean, but I still, I mean, I just want to advertise papers with this slide. I mean, I don't want to go into any detail. But what we can do is we can facilitate this dual unitarity also to make precise statements about operator spreading. In particular, we can compute Rényi-2 entropy of operators. So that means operator entropy for Rényi-2, which could be formulated by a similar dual unitary quantum circuit, but now with 4 replicas, right? You have 2 replicas for forward and backward, and then you have, again, another 2 replicas because you have order 2 already. Yeah. And then you use forward and dual fusion rules to simplify these circuits. At the end, you formulate things in terms of transfer matrices. And again, you can prove some statements or maybe more. I mean, there are some, results here that basically have sort of less rigor than the other results. So there are some things which you have kind of speculate, but it seems that, so they're conjectures, let's say. They're conjectures, which seems reasonable, but they're not proven. And modulo that conjectures, you find exact results on the scaling of Rényi-2 entropy as a function of, let's say, the key parameter in parameterizing dual unitaries, which is this coupling J. This coupling J was this coupling parameter here. For J equal to pi over 4, this is swap, it will be non-interacting. For J equal to 0, this will be maximally chaotic, which is self-dual Kick-Tisink. So J is a kind of key parameter which controls the degree of operator spreading. So there seems to be a phase transition in the speed of operator spreading from between maximal rate, and then at some critical value of J, it drops to 0 for swaps. And this is analytics, and the points are numerics. Okay, so now let me just address. Yeah, I probably have to just again use few minutes, 2-3 minutes to just address the computation of correlation functions for perturbed dual unitary circuits. I mean, I just try to pose the problem and for just tease you with one result. And I mean, that result, of course, is a very particular result, so it's not a general one, but still it promises that maybe there are more jewels in this model. So The first thing is, you can just, now these are non-dual unitary circuits. Now I will just, for that few slides that I'll show you at the end of my talk, I'll just assume I have a general circuit. So I mean general gate, and now I will use this folded picture, which means I will just, yeah, I mean this is, again, probably it's too quick for those who have never heard about the concept, but for those who have, it's obvious. So you just, formulate the correlation function by folding the circuit, like, that thing you can just fold back on itself, and then you get a simple correlation. I mean, simple propagation of states. Oops, let's go on now. Okay. Then you have simple propagation of states, but for double the Hilbert space. So the Hilbert space, which is now q bits, would be equal to 4. So these A and B are two operators, which are written in Pauli basis, if you want, and they correspond to 4 states per side. And this is the operator gate. Now, these operator gates, and now unitarity can be expressed simply like this, where this circle is the unit operator, and the circle above is taking the trace. So the trace is the dual to the unit operator in this picture. And well, dual, it's the Hermitian advantage. And then you can also have this dual contraction, which is the unitarity, which is dual unitarity. This is unitarity, this is dual unitarity. So what I will depict as yellow will be the dual unitary operator gates, and the green will be the general gates. So now this can be simplified sideways, but this can be only simplified vertically. Now this would be general correlation function, and just for clarity of pictures, we rotate by 45 degrees. And we make this wedge here just to designate orientation, because these things might not be left, right, and up, down symmetric, right? I mean, that could be manifestly breaking time reversal with space reflection. Now, what we try to do, and I just want to give you the motivation that we try to do. What we try to do is to perturb, let's say, a small fraction of the gates by writing them as dual unitary times e to the parameter times Hermitian operator, and considering this parameter to be small. And first, to make problem simple, we just perturb a small fraction of the gates. Let's just assume for simplicity, this is not the necessary assumption, but just simplifies that we perturb a regular sublattice of the gate, which is diluting the limit. So this means now we consider the limit of long time, large space separation, some higher than limit if you want. But then we also consider the dilute limit when we have a small fraction of the gates. Then the result which we hope for, and that result we can get, is that this correlation function basically now can be written as a sum over paths, where you basically have one dimension where each path is weighted by a one dimensional transfer matrix, which is like, taking the same transfer matrix as we. I mean, this is the same. I mean, just going from between two scatterers is the same transfer matrix as the one which we have. Is this completely positive trace prosemic map from above. It's just written in the folded picture. So basically, we have a fundamental propagator, which is this CPTP for one qubit, which is zero-dimensional dynamics. But then we just write a sum over those with respect to all possible scatterings over impurities, which are the perturbed gates. This is a non-trivial picture. I mean, you might think, okay, this is obvious, but it's not. I mean, you can have loops and stuff, but it turns out that under some conditions you have no loops. That this is exact expression. Now I have to stop, so I probably keep the rest for the discussion section. But I'm just, so I mean, yeah, probably I have to just. There is another convenient picture to think about correlation function, which is the tiling representation of correlation functions, and that only works under some simplification, which means averaging over some random transfer fields, which maps this quantum problem to a classical Markov chain problem. So let's say for Markov circuits, if you want. I mean, we believe that this is not an essential simplification, even though it is quite drastic because it maps quantum to stochastic dynamics. But then this correlation function can be mapped to tilings of the planar region with particular boundaries, which encode initial and final operators. And now these skeleton diagrams, which are sketched here, these sums of our skeleton diagrams now basically correspond to this non-loop tilings. Right, and now there is a statement which I probably don't even want to discuss in detail, but there is a simple statement depending on the parameters. Now, after this simplification, this averaging or random external fields, transfer fields in field direction, then your dual unitary or any folded gate now maps to a 4x4 Markov chain gate, which now means that you only map diagonal operators to diagonal operators. It is now fully decohered full circuit, So it's classical. So everything is just diagonal operators. So now again, local space is too deep because it's just identity in Pauli Z. And now you see, I mean, the dual unitarity now corresponds to the case. I mean, now this is just a way to describe dual bistochastic Markov chain in this particular representation. And the only thing that we require is that these two guys, these epsilons, I mean, are equal to 0. I mean, for dual unitarity or dual bistochasticity now, these two guys have to be 0. So these are basically parameters which control, I mean, which are linear functions of this eta. Right? So this is the key parameter. This is the coupling parameter for theory. So now we want to understand how the expansion works when we expand around the epsilons. And this epsilons basically gives you the weights of the terms. You see this tiling problem has these epsilons as terms. So just to give you an illustration, I mean, the second order, I mean, if you want to connect these correlation functions, this one to this one, you need at least 2 terms. So the lowest order is second order, but then you can have loops. Then the question is, under what condition you have no loops? And there is a simpler condition for that, and this is exact. So provided that there is inequalities obeyed between parameters, these are just A, B, C, D, E, F are just parameters of this averaged gate operator gate. Provided there are these particular inequalities among parameters, then you can bound the spectrum of this transfer matrix exactly such that you show that, I mean, basically you can show convergence of perturbation expansion under this condition in a nutshell. So I'm sorry, I mean, this is, yeah, I've been again, as usual, over ambitious of what I can say in 20 minutes, but that's, I'm happy to discuss with anyone interested. I mean, we are really excited about this because to my taste, to my knowledge, is the first kind of well, it's perturbative, but it's the other perturbation theory, which we hope it's convergent. So it's the first result on beyond dual unities, which uses dual unities as a skeleton. Okay, so this would be my conclusions. So I try to give you sort of overview of recent results on exactly solved models of many-body quantum chaos, results on spectral statistics, exact on spatial temporal correlation functions, and very briefly at the end on structural stability of perturbation stability of these models. Now there are things which I have not talked about, mainly because I have nothing to say, but there are interesting questions which we are working on, and we'll try to understand better. And the main kind of category of these questions is to provide finite size corrections to these results. So what are corresponding results in finite systems? I mean, of course, here you see, I mean, we had to take thermodynamic limits first. Whenever we did something, we had to take limit of spatial extent to infinity before T to infinity. We had to, move boundaries to infinity, essentially. Now, if you don't do that, then you have all possible problems. Then we can't do that. So far, we can't use dual unitarity, even though we feel somehow it should help. In particular, because we have recently a paper with Felix Fritsch, which is on the archive. I forgot to quote it. It's not a rigorous result, but it's a kind of intuitive result on decay of correlations in finite systems in relation to ETH, in relation to specular functions of local operators. And so it seems that you can have. I mean, it seems that there are kind of nice behavior of correlation functions in finite systems for derivatives, but we can't prove that. I mean, if you were able to progress here, we could probably prove ETH or at least non-unitaries. That seems to be still very difficult. What seems to be less difficult and more obvious is to extend these results to dual bistochastic Krauss circuits. So you can make manifestly dissipative quantum circuits with kind of Krauss replacing the unitaries and write precise conditions for things being Krauss in 2 directions, space and time. And most of the results I told you about follow straightforward. So with that, I would like to thank you. Sorry for being a bit condensed in the time.
Okay, thank you, Prosen. Thank you, Tomaz, for your very nice talk. We have time for a few questions. Okay, so it's I cannot see any raised hands. So let me ask. I mean, perhaps a unrelated question. I mean, another model for which you can, at least in the thermodynamic limit, you can compute correlation functions exactly, or to a certain extent exactly, is SYK, which is of course a very different kind of model with respect to this. Do you think there is any connection that is not easy to see, but maybe is there, or you didn't see anything?
No, I mean, I think it's really on the opposite end of the spectrum of models, in a sense. I mean, SYK is a zero-dimensional system, right? I mean, there's no
Yes.
And here we try to, I mean, that's kind of, SYK, it's, in a sense, it's easier because it's zero-dimensional. So you can make, it's also a random model, so you can use averaging. But I mean, here we try to really see what is the effect of local interactions on the number.
Right.
So that's the hard thing.
Yes.
So for example, I mean, yeah, and I don't want to go into unrelated results, but I mean, for example, there is a result which is kind of hybrid. I mean, this was our first result, which was the PRX in 2018 on long-range Kick-Dizit models. I mean, you can take a Kick-Dizit model with interactions which are long-range, but still non-mean fieldish. So with the power law decay of correlations, and power law decay of interaction with alphas, the power which you do. For that, you can do even simpler theoretical analysis. You can compute spectral form factor in terms of a 1D transfer matrix, not 2D, plus here. I mean, not 2D partition function, but 1D partition function. Assuming some things about, you know, this, or making some sort of random phase approximation. So that is kind of reduced dimension. I mean, I would call this a kind of reduced dimensionality. So that helps. So SYK is even better because it's 0D. So people not for SYK because it's 0D. But, of course, again.
Yeah, indeed. Indeed, the all-to-all property is really, I mean, the main feature that makes SYK solvable. So probably, I mean, in that sense, your result is much more, let's say, generalizable because somehow.
Yeah, it's not.
I mean, looks.
At least it explores locality, but of course it requires this dual unitarity, which is a strong condition, and simply in terms of simplification, it buys you a lot. But of course, it is not clear how expensive it is at the end. I mean, how much you can save.
And sorry, another thing that I didn't completely get is, for example, in the case of qubit system, is it classified the set of models that you can, let's say, achieve with the dual unitarity or not?
No, for the qubits, yes. I mean, this is what I showed you, right?
Exactly, yeah, but I didn't get it. So it is, for qubits, is classified. I mean, you can classify all the possible models.
For qubits, we have this. This is one slide, and I have nothing else to say.
Okay.
This is completely general. All possible dual unitaries for qubits are like this. They could be different. I mean, all these parameters could vary freely from any space-time point to any other.
Okay.
But that's what it is. So you use this parameterization, and then the only thing that dual unitarity fixes is that Jx, Jy, this is Heisenberg gate, and Jx, Jy should be powerful. Okay. And this is just free choice because you can use. I mean, these guys can encode any rotation as you do. Right? Sure. So you can use any other. So, I mean, of course, your question is much harder for QDITs. Actually, I posted last week a paper just, you know, I mean, playing a little bit with these ideas of what we can say about the manifold of dual unitaries for QDITs. It seems to be a rather complicated manifold with a complex topology. It looks scary. And another thing, I mean, which maybe it's not totally related to the question, but you can formulate all these models also in an alternative way in terms of IRF models.
Sorry, in terms of?
IRF, interactions around the phase models. So there is this second paradigm of classical statistical models. There are vertex models and then there's IRF models, right? And these quantum circuits are kind of related to vertex models. But, you know, you can also think of quantum circuits or quantum cellular automata being related to IRF models, which would be like, you know, gates which are control gates, which you just change a qubit provided that the boundary qubits, the H qubits, are in particular state. This is, for
I see.
example, related to PXP and the kinetically constrained model.
Yeah.
Right. So you can generalize all these models in terms of circuits, and there is an important or potentially important class, which is dual unitary IRF models.
I see.
So I mean,
sounds very interesting.
But that's I didn't see that. I just
okay. Other questions?
Okay. Can I ask a question?
Yep.
Sure.
Okay. So in the Hamiltonian system, if you have some local operator, then it will, expanding the operator helper space as a time of, in the course of the time evolution. And I'm not familiar with this unitary gate, but in your system, it seems that the operator growth is, kind of ballistic in time. Is that correct?
Right. It's what do you mean by ballistic? It means that it's linear in time, yeah?
Yeah, linear in time, yeah, ballistically. So,
which is complexity, which is positive complexity. I mean, it grows,
yeah,
number of components is exponentially growing in time.
Then can you compare this growth in your unitary circuit system with the Hamiltonian system?
Yeah, that's an interesting question. So, I mean, what we can compare directly is these results that people like Adam Manachum and other people got for random quantum circuits, or noisy random quantum circuits. And so, I mean, of course, it's hard to compare this directly to Hamiltonian dynamics because, I mean, this is, at least the Trotter limit doesn't really work. I mean, this is finite time step, but you can compare to random circuits. And the result for random circuits is roughly the half of this. So what people find for random circuits that the growth rate is log 2 times 0.5 or something. I mean, half of of maximum. This is Haar random. This is Haar averaged. I mean, this is a result for Haar random circuits, right? So you average over random gate. So now this is kind of remarkable that this kind of particular fine-tuned, if you want, class of models has stronger operator spreading than typical, hard typical random circuits. But that's not surprising again, because this, this is a kind of optimal for chaos, optimal for production of information.
Okay, thank you.
Okay, so maybe it's time to thanks Tomaz again for the talk. And yeah, we can take a 5-7 minutes break. And after that, we can start with the second talk. Okay, thank you very much. You can unshare your screen.
Thank you.